I'll record it again. I don't know. I didn't like the earlier recording. It was a little hit or miss. So, section 2.3 introduces that other operation on functions. We learned 4 operations last time. We have a 5th one that only belongs to functions, and it's called composition of functions. So that's a whole new symbol. We don't have composition of numbers, so we had to invent a new notation. So here it is. It's a little circle like that. And that stands for composition of functions. So just like you had addition, subtraction, multiplication, division, now it's something else. We define it as f of g of x. So that's the definition. So we're putting one function inside of another. Okay, so if we understand the function notation, remember all the smiley face examples? Those were compositions. Whatever goes in the parentheses replaces your variable. So in this case, g of x will replace every variable in the function f, whatever that is. We will call g of x the inside function, and we'll call f the outside function. And we'll do a bunch of examples where we're finding the composition. The really weird part about composition is finding the domain of a composition. So I'll explain this to you. I'll show you a few examples, and you'll probably see it on a homework or on the quizzes, but I'm not going to ask you on the exams to find the domain of a composition. It gets a little funky. Okay? But the domain, when you're taking the domain of the composition, will be, first of all the x's that are in a domain of G. So you plug in x in G, so G produces a bunch of other values, right? So G turns x from the domain into range, and then f has to be defined on the range of G. Because it's a 2-layer thing. You would say you throw in a 5 in for x, so first you get G of 5, whatever that equals to. And then you're trying to evaluate f at whatever G of 5 equals to. So G also has to produce values that f is okay with. Oh yeah, that's fun. So there are 2 layers of domainness of these functions. So anyway, so first of all, x is in the domain of G, the inside function. And G of x, is in the domain of f. But again, not a deal breaker at all. If you have no idea how to find the domain of a composition, you'll still be able to pass the homework quizzes, and I won't ask you that on the exam. It's a little silly thing. So let me do a simple example. Here's f of x equals x squared, and g of x equals x plus 1. So both functions are nice, pretty. Domain is all real numbers, right? Both of them. F is defined in all real numbers. G is defined in all real numbers. So as far as the composition is concerned, either way you compose these functions, the domain is going to be all real numbers. There are no issues at all here. Okay? So I can ask you to find f of g of x. And this is how we pronounce this, by the way, f of g of x. Which again means we're putting g function inside of f. That's what that notation stands for. That's what this operation does. And so What is the function of f? What does f do in life as it's defined? What's f's purpose as it's defined right now? What? Well, that's the general kind of a more like philosophic meaning of life type of answer. But very specifically, the way f is defined right now, the way it's written, what does f do? That very specific little f that I wrote, what does it do? Squares everything, right? Since I'm tossing g inside of f, g is going to get squared. That's what's happening. G is about to get squared. What is g? X plus 1. So x plus 1 gets squared. So that's the composition of f and g. So the g function went inside of f. But just like the smiley face, and we've done x plus h's and all that stuff. Whatever goes in the parentheses replaces the independent variable. Is that okay? What if I reverse the composition? What if I ask you what is g of f of x? So if I make f the inside function, what do you think that will be? X squared plus 1. F is going to replace the independent variable in g, so it becomes x squared plus 1. Because g is just adding 1 to whatever you give g to play with, right? Here's a bottle, bottle plus 1. That's what g does. So I'm giving g another function, f. F gets 1 added to it. Is that okay? What if I do f of f? X squared squared. Because again, you're thinking this is my outside function. That's set in stone for this specific example. It's just x squared. What goes inside? Well, another x squared. So x squared squared, which is x to the 4th. Is that okay? And the domains are just all real numbers. There's nothing to worry about. Any questions on how we do that? How we piece them together? Is that better than last time so far? Yeah? Okay. We're not done yet. We're just getting warmed up. So again, just to make sure, if I give you something like this, 2x squared minus 4x plus 1, and g of x is, I don't know, 2x minus 7. Again, the domains are all real numbers, so whichever way you take the composition is going to be all real numbers. But if I ask you f of g, what will that be? So every x, this used to be x, this used to be x in our f, right? F had 2 x's, so each x got replaced with g, right? So g goes inside of f, so replaces both variables in both places. So every time you see x in g, it gets replaced with, I'm sorry, every time you see x in f, it gets replaced with whatever g is. Is that okay? Now we can open up the parentheses, combine like terms. I don't feel like doing it, which you should do on whatever quizzes, homework, blah, blah, blah. There are extra steps to it. But as far as the composition, you know, that's about it. All right, good. Here's another example. F of x equals 3 over x, and g of x equals 2 over x minus 1. So what is the domain of f? Just the f function. Everything except for 0. All real numbers, so x does not equal to 0. Because you don't want to be dividing by 0. How about domain of g? Everything except for 1. Okay? So we should be okay with that. Now, before we move any further, let's talk about f of g, and let's find the domain of f of g before even computing f of g. Because the way we defined the domain of the composition function, first of all, it has to be the domain of whatever the inside function is. So what is the inside function right now, the way we write it? It's the g function, right? So we're starting with the domain of g. So right away, x cannot equal to 1. That's what we want, okay? Now, second part is that the values of g of x are in the domain of f. So now, what is the domain of f? As it's written over there. Everything's f of 0. So we really do not want g of x to turn into 0. If g of x turns into 0, then that's a problem, because 0 should not be in the domain of f, right? Because we're plugging values of g into f. So we need to make sure that g never turns into 0, because 0 is a bad number for f. So we have to solve an equation. Well, does g of x ever turn into 0? Because whatever solutions to this equation, we'll have to exclude them from the domain of the composition. So g of x is 2 over x minus 1 equals 0. Right? That's what g is. How do you solve such an equation? If you have a denominator, what should you do? Multiply by it. So multiply both sides by x minus 1. So that becomes 0. That cancels. So 2 equals 0, right? What does that mean? If you solve an equation, it comes down to 2 equals 0. Well, what's not in a domain? Well, remember what you do. You're trying to solve an equation so it becomes an identity, right? Yeah, 2 does not equal 0, so no solution. So since g of x can never turn into 0, we don't need to worry about that part. And again, think about this. G of x is a fraction. Fraction can only be 0 when numerator is 0, but numerator is 2, which is never 0. And actually, this is what it kind of tells you. It will only work if 2 equals 0, because that will be the numerator equals 0. And we know that's impossible. So no solution, so we're done. This is the domain, all real numbers but 1. Because again, you start with the domain of g, and then you're trying to add all the bad numbers that make g outside the domain of f. So this is a little tricky part. And it's a little weird, so it's, again, it's not that important. Don't worry about it. You might get a homework question with, oh well. Now to actually find the composition, f is 3 over x, and g goes inside of f, so that becomes 3 over 2 over x minus 1. Right, so I took the g function and I put it inside of f, so it replaced the variable. Now, this is an ugly expression. We should probably flip it, so that becomes 3 times x minus 1 over 2. Right, you just multiply by the reciprocal. So that's the composition. And the domain is everything but 1. Is that okay? Let's try it the other way. g of f of x. Again, the domain of this function, without seeing the function, we have to start with the domain of the inside function. The inside function is f, and the domain of f is everything but 0. So that's our starting point. Right away, x cannot equal 0. We're starting with the domain of the inside function. And then, what is the domain of g? Yeah, everything but 1. So we know that g gets really upset if there is a 1 on the inside. So we want to make sure that f of x does not equal 1. So let's see, can f of x equal 1? Well, f of x is 3 over x, right? So the solution to this equation is x equals 3. So that's another number that we need to look out for. Because when x equals 3, see what happens. If you plug 3 in for x into your f function, you get 1, and then you cannot plug 1 in there. You get 0 in the denominator. So we need to avoid this number. It turns f into something bad that g doesn't like. And actually, when we compute the composition, you will see that you're going to have some sort of a x minus 3 in the denominator. You will see that it's a problem. So the way we're going to do that, g is 2 over something minus 1, and that something is f. So 3 over x goes here. Is that okay? So that's the composition. F went inside of g. And I want to simplify that. So the way we simplify these complex fractions, you can always multiply and divide by the little denominator. You saw that trick last week. So that will clear out the little denominator. So when you distribute, 2 times x is 2x in the denominator. 3 over x times x is cancel. And then 1 times x is x. So you see that 3 is a problem for that function anyways, right? If x equals 3, it's 0 in the denominator, but we already excluded 3. So how's that? Good? Any questions? All right. Well, let's do this example. I'm going to give you 2 functions, and you'll just find the compositions, don't worry about the domain. So let's say one of them is a cube root of x plus 1 over 5. That's a 5. And the other one, g of x is is 5x cubed minus 1. Yeah. Something like that. Yep. So I want you to find the composition both ways and tell me what it is. F of g and g of f. So the setup, g goes inside of f, so we get a cube root of, instead of little x, we put all of g, so that's 5x cubed minus 1, right? That's the g function. And then plus 1 over 5. That's the setup, right? This is our little g function that went inside of f. And that's what you said, right? Yeah. or you did the other composition, which is also fine. So then we're going to simplify this. -1 plus 1, they cancel. So that gives you a cube root of 5x cubed over 5. So then 5's cancel. So that's a cube root of x cubed, which is x. Are you confident? Yes, okay. If it said square root of x squared instead of cube root of x cubed, if it was just a square root of x squared, would it still be x? What? If, hypothetically speaking, for whatever reasons, you coming down to this expression, what does that equal to? Well, square root of x squared. It does not equal x. Oh, forget about the q's. Square root of x squared. Now, well, one thing we need to remember that square roots, in addition to be, we can only fit square roots positive numbers. The square roots output only positive numbers as well. There's no square root of any number equals a negative number. Okay? Square root of 9 is 3. Well, you have to make sure it always comes out positive. Even think about this. If I ask you what is, don't write any of that down. The square root of -2 squared. If you just say square root of x squared is x, then the answer here is -2. If it's just x without any conditions. That's not true. If you follow the order of operations, what is the answer here? +2, right? Because it's -2 squared is 4, square root of 4 is 2. So the proper answer is absolute value of x. Every time you have even powers that match, it's absolute value. It always comes out positive. With the cubes, that's okay, because the cubics can produce negatives. This will come back and hunt you a little bit, so I'm just reminding you that that's actually a thing. That's square root of x squared is absolute value of x. Actually, it's about to come proper knowledge in chapter 3. So yeah, x, good. If we go the other way, it is 5 times whatever all of that stuff is. A cube root of x plus 1 over 5 cubed minus 1. Right, that's the composition the other way. So then again, order of operations, you're cubing the cube root. That gets rid of the cube root. So this becomes 5 times x plus 1 over 5 minus 1. Is that okay? So 5's cancel. So that's x plus 1 minus 1. So that's x. Okay. Now, if we try to put this in some sort of a bigger picture, I'm giving a little bit of a preview of what might come in the future. Because this is really interesting that a composition of two functions, two pretty messy functions, comes out to be something as nice as x. It almost means that one function does the exact opposite operations of what another one is doing. If you're getting an edge which you started with, that's what's happening. You put in the x, goes into one function, turns into some other mess, then it goes into the other function, and it turns back into x, so you're back where you started. If you think about this from a point of view of solving equations, because this is what you want to happen when you solve equations. You have some unholy algebraic mess equal a number, and then you want that unholy algebraic mess just turn into x, right? That's the whole process of solving equations. Big mess turns into x equals a number. Well, this kind of allows us to do that in one move, right? This is big algebraic mess. That's what f was. But then I apply g to function f, and it comes out to be x. Now, we will study those pairs of functions that kind of kill each other. And it's really going to become important when we start solving equations that are impossible to solve by basic algebraic rules, like, add 5 to both sides, divide by 7. That's no longer applicable. We have some weird looking functions. Well, we're going to have to kind of get creative like that. Just a little preview. Anyways. Good? Good. Next section, 2.4. We're going fast. So section 2.4 is dealing with symmetry, and I'm just again going to give you the highlights of that section, or what's important. There are 3 types of symmetry that we focus on in the graph. And actually, there are only 2 that we focus on, but there are 3 that I'll mention. One of them is symmetry around the y-axis, or with respect to the y-axis. So that means whatever's to the left of the y-axis is the mirror image of whatever's to the right of the y-axis. That helps us with graphing. If you have a function that, let's say, does this, and I tell you the graph of this function is symmetric with respect to the y-axis, can you finish the graph of that function? What do you think? Yeah, it's just kind of the same thing, only on the other side. So it's symmetric around the y-axis. So it's a mirror image. So we're actually going to learn how to make a prediction whether the graph of a function is going to have the symmetry, and then will help us with graphing down the road. Because it's easier to just graph half a thing and then let the symmetry graph the other half. Now, what's going on here is that you're always going to have a pair of points that are equidistant from the y-axis. So you either go in a negative x direction or in a positive x direction, same number of units, you're going to end up at the same height. Okay, so you're always going to have those pairs of points that it doesn't matter whether x is positive or negative, the y value will be the same. So it's either 5 or negative 5, the function produces the same result. So it's at the same height, and that gives us this pretty little symmetry. Okay? The other type of symmetry that we'll look at is a symmetry around the origin. So symmetry with respect to the origin. So that's where, again, if you have half a graph, the other half gets rotated around the origin 180 degrees, if that makes sense. So for example, if I tell you I have a function that does this, and it's symmetric around the origin, all I have to do is to take this shape and just rotate it around the origin 180 degrees. So I will get something like that on that end. So everything is rotated. Now, the way the points play over here, both signs change. If you start with a point, let's say it's negative x, positive y, you will end up with a corresponding point that has positive x, negative y. So both signs change, but still there's a relationship between them. So numerically they stay the same distance from x and y. Okay? So that's around the origin. Everything is rotated around the origin. The third symmetry, I'm not even going to write anything about that. It's a symmetry around the x-axis, so things like that. We don't care because it's not a function, so we don't talk about symmetry around the x-axis. It's not a function. Okay. All right. So now the important part is how to make a prediction. given a function, how can we say whether the graph is going to come out symmetric around the y-axis or symmetric around the origin? So that gives us these two fun definitions that you need to know. These are important definitions. We'll define a notion of an even function and odd function. So the definition of an even function, so a function f is an even function if and only if, and you remember how to shorten if and only if. Remember that? If f of negative x equals f of x for all x's in the domain of f. So this little line, the f of negative x equals f of x, suggests that it doesn't matter whether x is positive or negative, the values of the function are the same. So it doesn't matter if it's f of negative 5 or f of 5. Y's will be the same. So that gives you that symmetry around the y-axis. This is what I was describing here. It doesn't matter whether x is positive or negative, the values of the function will be at the same height. That's precisely what that says. Okay? So then even functions are symmetric around the y-axis. And I'll do examples how we can see whether the function is odd or even. Well, before I have to give you the other definition, that will be the definition of an odd function. So a function f is an odd function if and only if f of negative x equals negative f of x for all x's in the domain of f. So f of negative x equals negative f of x. So that's again going back to the graph that's symmetric around the origin. If you change the x, sign of the x, then sign of the y also changes. So it gives you the complete flip. So the odd functions are symmetric around the origin. Okay? So in order for us to test whether a function is odd or even, it has to satisfy one of these definitions. And both of these definitions start in the same place. F of negative x, f of negative x. So that's how we're going to start making those tests. You take a function, you put negative x in there, and then you just simplify. If after you simplify, you get back what you started with, then you got yourself an even function. If after you do the simplification, somehow you're capable of factoring out a negative, or it equals the negative of your original function, then you got yourself an odd function. And if something weird happens, then it's just neither odd nor even, so it doesn't have any pretty symmetries. Okay, so let me do an example. You know what I'm talking about. So example, determine whether a function is odd, even, or neither. So I'm going to start you off with this little guy. F of x equals absolute value of x minus 3. Okay? So odd, even, or neither. So in order for us to do that test, no matter what you think the answer is, that's irrelevant. You will start computing f of negative x. Because both definitions share that starting point. So that's what we're going to do first. And then we know function notation, so we understand whatever goes in the little parenthesis replaces the variable. This is kind of like composition right now. So it's absolute value of negative x minus 3. Okay? Now, you got yourself a minus sign inside the absolute value. Is that a certain level of redundancy? I mean, is it necessary there? What's going to happen to that negative? Yeah, it's going to go away. Regardless of what x is, that negative dies a painful death. So it's still an absolute value of x minus 3. It doesn't matter. Right? It doesn't matter. Well, that looks like what I started with, right? That's my original function. Absolute value of x minus 3, that's precisely my original function. So I'm done. I was able to establish that f of negative x equals f of x. So therefore, that's an even function. And it's symmetric around the y-axis. Right? I mean, I have f of negative x on one side, f of x on the other side. And there are a bunch of equal signs in between. I just picked on one of them. Doesn't matter. I mean, I do have established equality between both expressions. So therefore, f is even. How's that? X to the power 7 plus x. So again, in order for me to test whether this function is odd, even, or neither, I'm going to start at the same starting place by putting negative x on the inside. That's what we'll start with. And then we're going to see where the math takes us. So this becomes negative x to the power 7 plus negative x. So what's going to happen with the first negative? That's inside the power 7. Yeah, it's still going to be negative. So negative x to the power 7 is negative x to the power 7. So that negative sign kind of factors out. And then it's minus x, right? Is this the same as your original function? No, so it's not even. Can you factor a negative and make it look like your original function? In this case, it's pretty straightforward, right? If I pull out a negative, then it's x to the 7 plus x. And this is the original function. So it's negative g of x. Right? So therefore, function is odd. Sometimes it's hard to notice this factoring thing. Sometimes it's a little tricky. So when you get to this point, where you see this function is not the same as the original, therefore it's not even, you can separately, and this is an alternative approach, you can separately compute negative g of x. See what negative g of x equals to separately and see whether it matches what you get. Because if you compute negative g of x like that, you distribute the minus, it becomes negative x to the 7th minus x, so these two are equal. That's another way of doing that, because sometimes it's hard to just force it to be negative g of x. So just compute negative g of x on the side and see whether they match. So either case, g is an odd function. Is that okay? Any questions? No? Let's try this one. H of x equals x cubed minus 2x plus 3. So again, in order for us to test whether that function is odd, even, or whatever, we will have to start at h of negative x. That's the starting point. So every x becomes negative x. And then we're going to simplify this. So that becomes negative x cubed plus 2x plus 3. Is that the same as the original? No, so it's not even. Is this negative of the original? I mean, how can you say? This is what I mean by factoring a negative. It's a little trickier here. You have to turn pluses into minuses. So when in doubt, when you see that this function is not the same as the original function, compute negative h of x separately, and then see whether you match what you got. If you match, then you got yourself an odd function. If it doesn't match, then it's neither. So now keep in mind that if you compute a negative of a function, then every sign inside the function has to change. So that becomes negative x cubed plus 2x minus 3 if you distribute the negative. Is that the same as the original? No. It differed by one sign. This is the difference. So this function is neither odd nor even. So just a function. It doesn't have any, I mean, it has some symmetries, but we don't talk about that. So therefore, h is neither odd nor even. Is that okay? Another example. How about f of x equals x squared plus 5 over x cubed? So in order for me to test whether this function is odd, even, or neither, where do I start? Right, I need to compute f of negative x. So that becomes negative x squared plus 5 over negative x cubed. So what's going to happen with the negative in the numerator? Goes away because you're squaring it, so that's just x squared plus 5. What is going to happen with the negative in the denominator? Stays. So that's your entire denominator has a negative in front. Is this the same as the original function? No. Is this the same as a negative of the original function? Now let me ask you this question. Do you agree with the following statement? 1 over negative 2 is the same as negative 1 over 2 is the same as negative 1/2. They're all the same, aren't they? What do you mean? Well, they're the same. 1 divided by negative 2 is negative 1/2. Negative 1 divided by 2 is negative 1/2. Negative 1/2 is negative 1/2. So when you deal with fractions, It doesn't matter where you place a negative. I can always take the negative from the numerator or from the denominator and just put it up front. That still makes the whole fraction negative. So it is the same as the negative of the original function, negative f of x, right? Again, if you factor out negative out of the entire numerator or denominator, which we did, so the denominator only had one term, so therefore f is odd. Yeah? Actually, this is an interesting case because if you just focus on the numerator is an even function. Think about this. If you put negative for x, negative x squared kills the negative, so it's x squared plus 5. Numerator is an even function, right? And you saw that. Numerator just came back to where you started, while denominator alone is an odd function. So you have really a ratio of two functions. It was an even function divided by an odd function. And we can make a general proof that will show that every time you're dividing an even function by an odd function or odd function by an even function, the result is going to be an odd function. If you divide two even functions, it's going to come out even. If you divide two odd functions, what do you think will happen? Odd function divided by odd function. Even. Because you can factor out the negatives, and the negatives will cancel, make everything positive. So the ratio of odd functions is even. Well, anyways, that's a little... We actually wrote out proofs of that in the other group because they asked that question. Any other questions on this? What kind of symmetry does this function have? Origin, right? And let me show you. If I graph it, what was that function? X squared plus 5 over x cubed plus 5 over x cubed. So you see how it is? It's rotated around the origin. So this is a graph of an odd function. All right, good. Are you ready for 2.5? What? Well, you have a choice of being ready or not ready. I mean, I'm ready. So really now I'm going to be writing a lot. And I'm going to be writing a lot. I'm going to write one thing, I'll be copying and pasting it because I have that ability. You will have to write a lot. We're about to start building new functions from old functions by the means of transformations, just moving graphs around, stretching graphs, shrinking graphs, flipping graphs, just messing up with graphs. We're going to learn a total of 10 transformations. There are 10 different transformations you can do to a graph. Most of you have seen them before, again. At least some of them. The first ones I'm going to do, you've seen them for sure. But there is a general pattern, so you don't have to memorize all 10 transformations. If you understand a pattern, and then that's all you need to know is the pattern. And that's good, right? So section 2.5, and that's the end of chapter 2, is dealing with transformations. So there are a total of 10 of those. But before we dive into 10 different transformations, we have to build our little family of simple functions. Simple functions and simple graphs that go with those functions. So we know them and we can use them from now on. And you know most of it. So if I ask you, if you have this function, f of x equals x squared, do you all know the graph of that function? What is it? It's called a parabola, very good. So it's that looking thing. By the way, clearly symmetrical on the y-axis, even function, all that good stuff. Right? Because it doesn't matter whether x is positive or negative on the inside. So now you know this. From now on, that's official piece of knowledge. So that's the graph of x. I'm not going to be producing table of values because that's boring. How about the cubic function? F of x equals x cubed. What is the graph of that one? Does anybody remember? What are you trying to mime? Yeah. So when x is positive, you cube a positive x, you're going to get a positive result. So it's kind of like a parabola. But if you cube a negative x, you're going to get a negative result. So it dives down there. So it's actually an odd function, symmetrical around the origin. How about, and we already talked about this function, absolute value function. What is the graph of the absolute value function? V, we did that one. So now it's an official knowledge. I assume you know these shapes, that they connect those certain functions. Okay. Another one is the square root function. Who remembers the graph of the square root function? Yeah. It's a half a parabola flipped on the side. So it's like that. Right? It grows, still goes to infinity, but it's rather slowly. So now from now on, you know that's the graph. I mean, if we plot points, you'll get that picture. I don't feel like doing that. You know, domain is all non-negative numbers. And finally, the reciprocal function. 1 over x. Who knows the graph of a reciprocal function? Anyone? Come on, you 4 out of 4. Not quite. What is the domain of the reciprocal function? First of all, there are any domain issues? Yeah, 0, right? 0 is a problem. So that means the graph will never touch the y-axis. That's where x equals 0. And now think about this. So this function just takes reciprocal. So if I put a large number for x, 100, you take a reciprocal of it, you get something very, very small. So if x gets large, y gets small. So you get very close to the x-axis. At the same time, if you put a small number for x, 1 over 100, and you take a reciprocal of that, you get 100. So the closer you get to 0, the larger number, the larger y gets. Does that make sense? Because you just take reciprocals. Reciprocals of big numbers is small. Reciprocal of small numbers is big. So you get something like this. Right? You get really close to the x-axis. You don't touch the x-axis because you cannot take a reciprocal of a number and get 0. And you don't touch the y-axis because 0 is not in the domain. Now, look at this function. Is this an odd function or an even function? Or neither? What do you think? Just do this test in your head very fast. Odd, right? If you replace x with a negative x, you're going to get negative 1 over x. So by the oddness of this graph, it's symmetric around the origin. So here's the rest of it. Just rotate around the origin. So this is the reciprocal function. We're good? So these are the family, definitely first 4. You all know how to graph a line, so that's another family of functions, the lines, but you graph them differently, max plus b type stuff. So now, don't write this down. We're going to talk. I'm going to try, very good. I'm going to try to at least get an early attempt at the pattern that you will see. And this is a quite wonderful pattern. I was proud of myself when I noticed it. Wasn't right away. I made former generations of college algebra students to memorize these 10 transformations. You're one of the lucky ones. Just past few years, I was explaining this through a pattern. So, notation, f of x. Where is the independent variable in there? x. X is the independent variable. On the graph, on the axis, your 2D plane, where is the independent variable? Which axis represents the independent variable? The horizontal axis or the vertical axis? Horizontal, right? That's your x-axis. The x-axis is your independent variable, right? So we're going to mess with our function. So every time you mess directly with x, you're messing with independent variables. So all changes will occur along the horizontal axis. It will not affect anything vertically, only horizontal axis. So if you mess with the x, changes occur horizontally. And that makes sense, right? At the same time, the values of the function, the whole f of x, that's really the y value. That's your vertical axis, okay? So every time you start messing with the whole function, you add a number, you multiply it by 5, you're messing with the y values, so all the transformations occur along the vertical axis, okay? Mess on the inside, mess with the x, changes are horizontal. Mess with the y, mess on the outside, changes are vertical. So that's one part of the pattern. And that's the cheap part. That you can figure that one out. Another part of the pattern that you will notice, again, if you mess with the y, you mess with the vertical axis, whatever you think should happen is probably true. Whatever your gut feeling, the first, the common sense tells you, hey, that's where the function is going to go, that's true. That's where the function is going to go. When you start messing on the inside, whatever the common sense tells you to do the opposite. And you will see that. So there's going to be this kind of pattern. When you mess with the y's, everything makes sense. When you start messing with the x, it almost fights you. Everything that you stand for becomes false. So just do the opposite. Whatever urge you have, do the opposite. Unless you get really good at it, then stop doing the opposite. Just do whatever you think is proper. All right. So here are the 10 transformations. So first of all, let C be some positive number, and the graph of y equals f of x is known. So we're starting with a function, the graph of which we already know. So it's either given to us, or it's one of those little functions that we did earlier, from our family of functions. So the graph of f is already known somehow. So here are the transformations. The first list, we'll call them the vertical shifts. So in order to sketch the graph y equals f of x plus c, and I'm going to continue the sentence, but let's think about what I'm writing here. So this is a function that the graph of which I already know, f of x, and then I'm adding c to it. So I'm just adding some constant. Am I messing with the independent variable on the inside, or am I messing with the dependent variable on the outside? Dependent, right? I'm adding something to the whole function. So that means I'm adding a constant to all the y values. So if each ordered pair gets a number added to the y, what happens to every ordered pair then? Yeah, everything just jumps up by c units. And this is what I mean by common sense. You're adding something, so everything gets bigger, so everything just went up, right? Each y value increased by whatever c is. Let's say you're adding 2, so every y value went up by 2. So that means in order to sketch the graph y equals f of x plus c, we need to shift the graph y equals f of x, c units upward. Okay. And I'll do examples of it a little later, but a vocal example, x squared plus 2. You know the graph of x squared, it's a parabola. You're adding 2 to it, just everything went up by 2, so parabola jumps up. Good? So, if instead of adding a number, I'm going to subtract a number, what's going to happen with the graph? It's going to go down by whatever number of units it is. So this is where you have to write a whole new sentence, and I'll just do copy-paste. Oops. Come back here. So I'll just do that. I'll just have to change a few words. I will have to change, well, first of all, number 1 to number 2. I have to change plus to minus and upward to downward. So these are the new words. So this is minus c. This is downward. So again, you start with the function that you know the graph of, and then just subtract a number from that function, so the graph just drops down. And most of you knew that before you met me, right? I mean, that's nothing really extra crazy. But that goes, again, think about that pattern, because this is the easy example, think about the pattern. Masked with a function, therefore changes are along the vertical axis, and they are kind of intuitive. You add stuff, it goes up, you subtract, it goes down. Kind of what you expect to happen. Is that okay? So the next group of transformations are horizontal shifts. So again, I'm just going to copy the thing I wrote before, and I'm going to show you what I'm changing in there. And we'll discuss it. So don't write the rest of it, but in order to sketch the graph of y equals f of x plus c. Now notice the difference, how I'm adding a constant on the inside. Right? So I'm messing with the independent variable, I'm messing with the x, so all the changes occur horizontally. Now, especially if you've never done this before, because those of you who've done this before know where the shift probably occurs, but what common sense suggests? If you add something, where it should go? To the right, do the opposite. So it goes to the left. That's the pattern. So when you add a number on the inside, the function actually shifts to the left. Okay? So we're adding it actually going to the negative side. And again, let me just show you a very quick example why that's happening, so that will make sense. But you see what I mean by counterintuitive? That's what happens with your circles. If you look at the circle, x plus 2 squared, the center is at negative 2. Right? What? Are you sure? Yeah. Okay. Think about this. This is x squared, right? And I want to try and sketch x plus 2 squared. So we have this point. The original function has a point 0, 0 on it. When x equals 0, y equals 0, right? That point is called the vertex. Well, now let's think about what is the vertex of that new function. What does x have to be in order for the y to equal 0 when it's written like that? What does x has to be in order for this function to equal 0? Negative 2. So this is why it actually shifts to negative 2. So it's 0 at negative 2, and then it grows out of there. See that? So that's kind of what's happening over there. But again, if this makes sense, what I'm saying, by kind of the opposite of what intuition suggests, then we're kind of good. All the horizontal shifts. Okay. So the fourth option is if instead of adding, we are subtracting. So f of x minus c. So then shift the graph c units to the right. Again, you mess on the inside, you mess with the independent variable, changes occur horizontally in an opposite type kind of order. So if you subtract, you go to the positive side. So you have to offset of what you just did. When you mess with the domain, domain shifts in opposite direction. So that's 4 out of 10. Well, that's good. Let's do an example. So I want us to sketch and find domain and range. Because again, remember, we can always find the domain, but in order to find the range, we need to see a graph. So a quick sketch, we don't need to have a precise graph, but a quick sketch helps. So that's what we're going to do. And the function that I want to play with, let's say f of x is absolute value of x plus 3 minus 1. So here's the function. So we always start with the function that we know how to graph. So what do you think, which graph are we messing with here? Which function is our starting point? What are we going to be shifting around? What? But what is the shape? Yeah, the absolute value. This is our starting point. So we will start messing with the absolute value function. So here it is. So that's the absolute value, just absolute value of x. Where is it going to go? So it's going to go down 1 because of the minus 1 on the outside. So I can do that. So 1, 2, 3. Yeah, so it goes down 1 over 3. So this point is negative 3, negative 1. Right? Because I'm adding on the inside, right? I'm adding directly to the variable. So this is that story. So going to the left. So again, this is what I mean by opposite of what feels right. What is the domain of this thing? Yeah, just all real numbers. Because again, we don't need to see the graph for that. That's just a normal function. You have a question? Well, because it had the absolute value, so I'm just trying to match it, which one, is closest. If I had same thing squared, I'll be shifting a parabola around. If this was x plus 3 squared minus 1, it would be a parabola starting at that same point. Now, what about the range of this thing? So you're looking at the y-axis. What? Well, there's no graph in this region from negative 1 to infinity, including negative 1. So you're just looking at the y-axis, what's covered on the y-axis. Okay? Any questions? So these are our first 4 transformations. Now the other 2, they don't really have that go the opposite direction of what makes sense. They're going to just make sense, I think. So the other 2 are reflections. So I really have to put some changes here. So this is number 5. Now what I'm trying to sketch is negative f of x. So I'm putting a negative in front of the whole function. So before we finish the rest of this story, first of all, am I messing with the independent variable or dependent variable? Am I messing with the x or with the y? What? Dependent, right? Independent if I'm messing on the inside, dependent I'm messing on the outside. So that means I'm changing the sign of every y value of every point. So all the positive y value, all the points with positive y value now have a negative y value. And all the points with negative y value now have a positive y value, right? So the whole graph kind of flips over. The bottom becomes top and the top goes on the bottom. So that, what is it going to flip over? Is there an axis of flippage of this graph? Yeah, it's flipping over the x-axis, right? So then, in order to sketch the graph of y equals negative f of x, we will have to reflect the graph y equals f of x over the x-axis, right? But again, the changes occur along the y-axis. That's where the changes happen. Positives became negative, negative became positive. The x, the domain, is not being affected at all. Actually, range is not being affected, but it flipped. Okay. So, in the same token, we have the 6th transformation. So now instead of putting a negative on the outside, we're going to put a negative on the inside. So that's number 6, f of negative x. So we're messing with independent variable right now. So the changes will happen along the x-axis. But again, think about this. So the ordered pairs that have a positive x value will now have a negative x value. And the ordered pairs that have negative x value have a positive x value. So this is what happens. So then again, we have a reflection over what? What is the axis of reflection here? The y-axis. Okay. So then we have to reflect the graph y equals f of x over the y-axis. Okay? So again, I want us to sketch and find domain and range. So here's the function f of x equals negative x plus 2 squared minus 3. So what is our parent function here? What are we messing with? Probably, right? Because of the square, we're going to be messing with the shape of the x squared. This is our starting point. This is the graph that is known. And then we'll apply all the transformations to it. Now, we have to be very careful. When you have multiple transformations, because here we have 3 transformations, it's actually possible to get the wrong answer if you do the transformations in the kind of a strange order. You can misinterpret what happens. So the way to get the right picture every time, just follow the order of operation. And if you do the order of operation, you do your transformations in that order, you'll get it right. So order of operations, parentheses first. So we're going to deal with the parentheses. So plus 2 on the inside. Where's it going to move the graph? Left 2 units, right? So I can take this graph. I guess I cannot. I'll have to do it slower. Have to wait. And then if I do the parabola, now I can probably shift it. So if I take the parabola, can I take it? Yeah. So 2 units to the left, right? Then by the order of operation, technically it's exponents, but all that the power does, it tells us it's a parabola. So next step is the multiplication, so that's that negative in front. What is the negative in front going to do? Flip it over the x-axis, right? Now, this is going to look weird the way I flip it over the x-axis. Still need to track it down, so here it is. Right, that's flipping it over the x-axis. And then, what is minus 3 going to do? Down 3. 1, 2, 3. So this point right here is -2, -3. Domain is all real numbers, because there is no issues there. We don't need to see the graph to answer the domain question. But what about the range? What is the range of that function? Right, so it's from -infinity to -3, including -3. So it gets there. Is that okay? All right. Well, this is a fun example. F of x equals negative square root of negative x. So what is our parent function? What shape are we going to be messing with? What graph that we know? The square root, right? So in this case, it doesn't matter in which order you do your reflections, but this is what you start with, right? So what's going to happen with that graph? It's going to flip over the y and flip over the x, right? Or it's going to flip over the x and flip over the y, regardless of the order in which you do your flipping. It's going to come here and then go, oh, I should use a different color, go there. Or you flip here and come there. It's still the same picture, right? The green one would be the answer. So it does 2 flips, over the y and over the x, or over the x and over the y. Same result. How's that? Is that good? Yeah, so that's 6. 4 more. We're almost there. 4 more. So now we're going to talk about stretches and compressions or shrinking, I don't know. Stretches and compressions, I don't know. Either way you want to call it. We're going to make things bigger, we're going to make things smaller. So I'm going to write a new sentence. So that's that's a rule 7. So first of all, let C be greater than 1. So not just that constant is positive, it's actually bigger than 1. So in order to sketch the graph y equals C times f of x, we need so what are we messing with? Dependent or independent variable here? Dependent. We're messing with the y values. And we're multiplying the y values by a number bigger than 1. That's what this says. What will happen to the y values if you multiply them by a number bigger than 1? You get bigger, right? So if every y value gets bigger, what's going to happen with the whole graph? Yeah, it kind of stretches vertically, right? Becomes skinnier. Let me show you this. if I do just a regular parabola, okay, and then I'll do another parabola, let's say 2 times the parabola. Let's make this one red. So the red is the original parabola, and the black is 2 times the original parabola. So it kind of got skinny because every point got doubled. Because look, this is the point on the original parabola, y equals 1. You multiply it by 2, now y equals 2. This point on the parabola, y equals 4. You multiply that by 2, it's going to jump all the way to 8. Doesn't affect the x values, because look, you will have a point that goes through 8 right there. See, this is 4, got doubled. So everything gets doubled. The x-intercepts don't care, because the y equals 0, so you double 0, you still 0, right? And if you increase, if you go from 2 to, let's say, 3, that's even more, right? The blue one, even steeper, or 3, 13, even steeper. So it stretches the graph vertically. So this is, again, the kind of common sense. You multiply by bigger than 1, things get bigger. You stretch the graph. Okay? So what will happen if it's less than 1? What do you think? Yeah, if you, instead of multiplying by 2, you multiply by 1/2, it gets a wider parabola. 1/13th, for whatever reason, it's really wide parabola. So it compresses vertically. Okay, so every y value gets divided by a number. So let's write that up. So we need to stretch the graph y equals f of x vertically by a factor of c. And what that means, if c is 2, you double everything. If c is 3, you triple everything, and so forth. That's what we mean by a factor of c. Is that okay? So then we already talked about transformation 8. If c is less than 1, then everything will shrink vertically or compress vertically by a factor of c. So let's write that one down. So we will change 7 to 8. We'll say c is less than 1. Yeah. Well, c is greater than 0. That's what we said originally, but yeah. You're right. Because if it c is less than 0, then it will flip and stretch or shrink. So if you think, so this is 8. C is between 0 and 1. So then we'll need to shrink or compress the graph of that vertically by a factor of c. So things get lower. It's really fun to see that with functions that, not just parabolas, but, I mean, I'll show you a few examples. But again, it follows that pattern. You mess with the dependent variable, so all the changes occur along the vertical axis, and they kind of make sense. Bigger than 1, stretch, make it bigger. Less than 1, shrink, make it smaller. Okay? Still works with the pattern. Now, the last two, so you probably know what I'm going to say already. So we're going to change 7 to a 9. We will put so 9, and now I'm doing f of c times x. So now we're messing with the independent variable, right? But when inside the function, we're multiplying x by bigger than 1. Based on our pattern, we know how to fill in the rest. bigger than 1, first of all, independent variable, we're messing in the horizontal direction, right? Because that's the x-axis. And whatever our intuition suggests, we should probably do the opposite. So if we multiply by bigger than 1, the intuition probably tells us to stretch it, right? If it's bigger than 1, make it bigger. Well, do the opposite. So it'll actually compress the graph horizontally, okay? So we need to compress or shrink the graph horizontally by a factor of c. And we will not notice this with parabolas, but if you have a function that has multiple x-intercepts, then you're really going to notice this shrinking or stretching. And let me write part 10, and then we'll start doing examples. So part 10, you're going to make it less than 1, so again, do the opposite. It will stretch it horizontally. Oops. Oh, yeah, I don't need that. I already have it here. So the final transformation. So transformation 10, c is between 0 and 1. We want to do f of cx. So it will do the opposite of what we think should happen. It will actually stretch the graph horizontally by a factor of c. So if you forget how to do those transformations, just remember that pattern. Ask yourself, are we messing with the x or with the y? And then if you're messing with the y, kind of go with your gut. If you're messing with the x, well, kind of do the opposite of what your gut suggests, if you forget. I mean, if you remember, then your gut will tell you the right things, but don't do the opposite. So that might be a mess. Now, some of you at some point have seen a trigonometric function. You might have seen a sine function. How many of you have seen a sine function or cosine function? We're not going to study those functions here, but they have very nice graphs that will illustrate whatever it is we're talking about. So if I just do sine of x, now this is the graph of a sine of x. Very nice, very pretty, very wavy, and so forth. So if I try to do this function 3 times sine of x, can you predict what will happen with the graph? Which way? Right. I'm multiplying the function. I'm not messing with the x. I'm messing with the y, so everything will get triple, right? So if I actually do that, that's what happens. If I just add the sine x as a reference, so everything's stretched vertically, right? That's what our rule suggests. If I go 1/3, everything will shrink vertically. Okay? At the same time, if I put 3 on the inside, what will happen? Yeah, it will compress it horizontal. So actually it will increase the frequency of that graph. That's what happened. So it started doing it 3 times as fast. Because again, the x value kind of come into your function 3 times faster than before. So we can increase the frequency, or we can decrease the frequency by going 1/3, something like that. So it's really kind of stretched out sine curve. See that? But again, we don't need to know any of those functions, whatever. Those are just pretty graphs. And you can see how those numbers play. And if, of course, I toss in a negative in front and go +6 and -4, we'll still get a graph. You know, it shifted. Elsewhere, it got flipped. So there are many things that just happened to that graph, right? it got stretched, it shifted to the left, it shifted down, and also got flipped. Right? If I put a negative again in there, it might get flipped again. So, you know, that's what just happened. Isn't that fun? So yeah, foo plot, that's what I was telling you before, but that day it didn't work. Today it works, so hey, nice. Okay, so let me do a few more examples where we use this. So let's say we're starting with the graph. Not drawn to scale, but so here's the graph. This is -2. So this is the graph of f. What? So that's what I mean by graph of f is known. So it's some ugly thing like this, or one of the pre-functions that we know already. So I want you to sketch, let's say this function, y equals f of x, and we're going to multiply f of x by 2. Okay? So what happens to the graph if you multiply the function by 2? The whole function. What are you messing with? X or the y? The y. So along the y-axis, so everything will get doubled. And the easy way to do that, if you have your x-intercepts, they're going to remain x-intercepts. Because you double the 0, it's still 0. But this point, -2, 3 will become -2, 6. This point, 3, 3 will become 3, 6. So the graph will actually do something like that. It's just stretched vertically by a factor of 2. Right? Every y value got doubled, with some extent of accuracy, but that's the idea. What if I ask you y equals f of 2x? What will happen? Stretch or shrink? Shrink. So every x value now gets divided by 2. So that means -4 will shift to -2. -2 will shift to -1, while the heights will stay the same. So you actually have this effect. Right? So this point went closer to the origin by half. This point went close to the origin by half. The heights don't change. The x, that intercept of the origin doesn't change. Now this point, 6, will become 3. Right? And the 3 here will become 1.5. So it will do something like this. So this is the new graph. It just went by half. So every x value got divided by 2. Right? Because again, if you go backwards, let's say 3, you take 3, you plug it in here, it becomes f of 6. Well, f of 6, that's the original function. F of 6 is 0. That's why those points kind of get closer to each other. Okay? But just remember the pattern. If you mess horizontally, kind of do the opposite of what feels right. If you shift vertically, then do whatever you think is right. But don't just claim that on a test. Like, well, I thought that was right, and you told me if I think it's right, it's right. But, there's an extent to that. Does that make sense? All right, good. Well, that's chapter 2. Well, that was fun.